Yes, hello folks. We are here with the exercise 5.8 part 1 video. Like always, some problem happened and the entire recorded video was I don't know where it went. So it's very difficult to write all this again. So we will just go over it once and then from next part onwards we will write it freshly. Now in this exercise 5.8, we are going to see two concepts, that of Rolle's theorem and Lagrange's mean value theorem. It's also called as mean value theorem. Now what are these theorems? There are some conditions. When those conditions are applicable, you are able to apply the theorem. So that's how it is. We are going to see those things over here now, and we'll see the conditions and we'll see how we can apply it to the problems. So the first Rolle's theorem, the condition that is there is f is continuous on the closed interval AB. AB is an interval where the function is defined. And if f is, that's a condition number 1. Condition number 2, f is differentiable on the open interval AB, and if f of a equal to f of b, f of a equal to f of b. If these three conditions are applicable, then in that case there exists some c belongs to the open interval AB such that f dash c equal to 0. Okay, so that is the Rolle's theorem. If at all the condition number 1, 2, 3 is applicable, then f dash c will be equal to 0, where the c is belonging to that a and b. So that's how it is. Now geometrically, if you want to understand that condition, what does it mean that this is your function, the curve is given by the function, and f dash c equal to 0 means if you draw the tangent at this point c, then it will be parallel to the x-axis. That is the meaning. So that's about the Rolle's theorem. Now mean value theorem sometimes is also called as Lagrange's mean value theorem, and its conditions are condition number 1, same like the before one, continuous on the closed interval AB and differentiable on the open interval AB. Then that clause is not there. Then what happens is there is some c belonging to the open interval AB such that f dash of c equal to f of b minus f of a by b minus a. Now this is a little more general. In this case, we had to have the point C which would be parallel to the x-axis. But here you will have that C which will be parallel to the chord of the curve. Now how do we understand that? Suppose if you have a function like this, in f dash C, there is some point C and we are drawing the tangent, that's how we are getting f dash C, slope of the tangent. This is parallel to this chord. How did you get the chord? You have taken the point A, you have taken the point B, you have taken its y coordinate, you have taken its y coordinate. So this chord is any segment that is formed by joining two lines of the curve. So 2 points of a curve. So we have taken these 2 points and we have joined it. So that's how we have got this chord. Now we are taking the slope of it. The slope is y2 minus y1 by x2 minus x1. That's how we have got the slope of this chord. Slope of this chord is equal to the tangent, slope of the tangent. When they are parallel only that happens. So they are parallel, and that is why the slopes are equal, and that's why we are able to get this condition. So that is a geometric interpretation of mean value theorem. Now this is what we are going to apply in our problem number 1. Now problem number 1 says they give us a function fx which is x squared plus 2x minus 1, and this x is belonging to the closed interval minus 4 and 2. They are asking us to check whether Rolle's theorem can be verified. So for that, what we will do is we will check if all the 3 conditions are first of all applicable. So we are checking gradually. First we have taken the function f of x is x squared plus 2x minus 8. This is a polynomial function. Yeah, we all know it's a polynomial function. So every polynomial function, we have learned in our continuity chapter that polynomial function, trigonometric functions, wherever it is defined, such things, they are all composition of functions, they are all continuous in the interval where it is defined. So this being a polynomial function, it is continuous. There is nothing to break your head on it. Yes, it is continuous on the given interval. Then we look, second condition is differentiability. So for that we will take the differential of this given expression and it comes out to 2x plus 2. Now this also is a polynomial function. So on the interval where it is defined, wherever it is mentioned, there it will be existing. Yeah, differentiability means whatever differential you are getting on that given interval, it should exist. Yeah, so it is existing on that interval, and therefore it is differentiable on minus 4 to open interval. Then we have to check the function on the extreme points. So f at minus 4, we substitute it over here, minus 4 squared plus 2 times minus 4 minus 8. When you solve it, it comes to 0. So also we will find out f of 2, that is the other extremity. we try to substitute it, there also you are getting the value as 0. So this condition is satisfied, f of a equal to f of b. That condition is getting satisfied. As a result, by Rolle's, you are able to apply the Rolle's theorem, and by Rolle's theorem, let f dash c be equal to 0. Now how do you get f dash? You already have the f dash. So f dash c is 2c plus 2 equal to 0. Let's try to solve it. You are getting the c value as minus 1. Now this minus 1 is definitely between minus 4 and 2. That is our verification point. Whatever c that you get, it should lie in the specified interval. Then only you can verify the Rolle's theorem. So we have got it lying in that interval. C equal to minus 1 is belonging to the open interval minus 4 2, and therefore Rolle's theorem is verified. So this is how you verify the Rolle's theorem. Quickly go to the question number 2, which has got 3 subparts. In these 3 subparts, they are asking us to check whether the Rolle's theorem is applicable. That means what? The question itself suggests that there must be the 3 conditions. Out of the 3 conditions, some condition would not be obeyed. That is why they have asked check. Okay. So what I would suggest is, rather than doing continuity, whenever you get such questions where they ask you to check Rolle's theorem, rather than going in for condition 1 and 2, directly go for condition 3. And if the condition 3 is not it is getting obeyed, then only go for condition 1 and 2, because condition 1 and 2 sometimes it's difficult to express, or sometimes there are lots of steps that you have to write, whereas this condition 3 is very concise, it's very precise, you know what to write. Right, so it is more easily expressible. So we will go for the condition 3. By chance, if it doesn't work, then only we will go for condition 1 and 2. Always keep that in mind. So that's what we are going to do here. Your first function is given as a greatest integer function, which is lying between 5 and 9. So we'll check the extreme points. That means we'll check for f of 5 and we'll check for f of 9, and we'll see what happens. F of 5, greatest integer function, we know for every integer it's itself. So 5 is an integer, so it's itself. F of 9 is an integer, so it is itself 9. Now both these values are not same. They are different. Because they are different, Rolle's theorem is not applicable, because if the Rolle's theorem has to be applicable, f of a has to be equal to f of b. That doesn't happen. So that is why Rolle's theorem is not applicable. So that's how it is. Same I would suggest for the next problem also. Let's check the extreme values. Here also the extreme values are minus 2 and 2. You know it is an integer. F of minus 2 is going to be minus 2. F of 2 also is going to be 2. They are both not same. They are not same. So Rolle's theorem is not applicable. Right. Your last one is f of x equal to x squared minus 1. There also we will check the extreme values, f of 1 and f of 2. F of 1 when we substitute is 1 squared minus 1, which is 0. Then f of 2 when you substitute, it is 2 squared minus 1, which is 4 minus 1, 3. Here also f of 1 is 0, but f of 2 is 3. They are not equal. So that is why you cannot apply Rolle's theorem in all the 3 cases. Okay. Now there is an extension in the question which says that you just check if the converse is applicable or not. Converse is applicable just the other way around. That f dash of c is 0, then condition 1, 2, 3 whether it is getting obeyed or not. So, but the problem here is that when we think of applying the converse, we are taking f dash of c equal to 0 as given. That we have to take, where c is belonging to 1 and 2. Now, for that, when we start for the first problem, if f dash c equal to 0, you have to start like that. Okay, converse means you are given that f dash c equal to 0, and then you have to check condition 1, 2 and 3. So, suppose say it's given to you that f dash c equal to 0 for c belonging to 5 and 9. Now, you have to specify this. What is this f dash c? So when you look at the function, greatest integer function, you know that when f of x is the greatest integer function, at all non-integer points, f dash c is 0. At all non-integer points. So because only at integer points, I don't know whether we remember the graph. The graph was like this. This way. So it's like at all these points, it is parallel to the x-axis. So wherever the curve is parallel to the x-axis, so the slope of the tangent wherever it is parallel, there the slope of the tangent will be 0. So here all it is that way, here all it is that way, here all it is that way. So many points where this c is happening. They are asking us to take one c or where that happens, and here there are so many c's where this is happening. So there are many points between 5 and 9 where f dash c is equal to 0. So we are not able to apply the converse because the given itself you are not getting through. You are not getting a proper way of getting the given. Come on, f dash c equal to 0 at c is so much. We are not able to tell that. right? So that is why we are not able to apply the converse, because we are not getting through the given properly. So we abandon that. Second one is also the same. The only thing, the interval is changing. So you have to apply the same logic except for the interval change. So there's no need to for us to just write that same thing again. It's the same as above. Now in the third case, we have to take f dash c equal to 0. So f dash c equal to 0 for some c belonging to 1, 2. So this c we have to give it. You have to tell them, come on, this is your c. Now check condition 1, 2 and 3. So for finding out that c, we are first looking at the function x squared minus 1, f dash x is 2x. So your c could be like f dash c is 0 is your condition. So your c has to be 2c equal to 0, which makes the c value as 0. Now see the problem, the c that you have got over here, earlier case we were not getting the c only, here we have got a c, but that c is not lying in the open interval. It's very necessary that c should lie in the given open interval, but c is not lying in the open interval, it's lying outside. So what happens, your given is not perfect, okay? Unless your given is perfect, you cannot explore into other things. So we are not able to apply at all. Okay, when we are not able to get through the given, for such a case we are not able to apply it. So converse doesn't apply for all the 3 cases, right? So that's our question number 2. With the question number 3 we meet in the next video. Thank you.